Okay, so question number 5 on test 4 is asking us to, upon complete combustion, how many milliliters of ethanol are required to produce 14.5 liters of water vapor at 25 degrees Celsius in 1.03 atmospheres. Okay, so this is going to involve the gas law again. So PV equals nRT. Now, first thing we do is we need to find that 14.5 liters of water vapor at a certain temperature and a certain pressure are going to equate to a certain number of moles. And then from there, we can solve. So we're given pressure, we're given volume, we are given T, and we know R by default. So once again, just like last time, we have N is equal to PV over RT, which is equal to, the pressure is 1.03 atmospheres times 14.59 liters over R, which is 0.0821 times, and now we got 265 degrees Celsius. It needs to be in Kelvin, so we just take the 265 and add 273 to it, and that is going to be 538 degrees Kelvin. So when we multiply that through, we are going to end up with 0.34 moles of H2O. The next step we need to do is we need to balance the chemical equation. So ethanol, the formula is given to us. It is C2H6O. It is given, and then we know we're going to burn it in oxygen, and we're going to end up with water, which is what we're interested in, and then CO2. So here we can balance this. The last question I showed you how to do it. This time I'm just going to write it like this. So we had one of these, three of these, 3 waters, and 2 H2Os. So there, now we have our stoichiometric ratios for each species in the reaction. So going back to this 0.3 moles of H2O. So 0.34 moles of H2O. We have 3 moles of H2O is equivalent to 1 mole of ethanol. And we get that from our stoichiometric ratios, right? 3 and 1. And the 3 goes on the bottom because we want moles of H2O to cancel out. And what we're going to find out is that's going to be equivalent to 0.1134 moles of ethanol. I apologize for this line appearing. I don't know why it keeps doing that, but it does. Okay, so now that we know how many moles we have, we can find out how many grams we have. And because we are given the grams, or we're given the density in this problem, we're able to find out the milliliters. So if we have if we have 0.1134, and that's moles of ethanol, the molar mass of ethanol, so 1 mole of ethanol is equal to 46.08 grams, which comes out to be 5.23 grams of ethanol. Now, remember, the equation for density is equal to mass over volume. So now we know density. Density is given to us. It is 0.789 grams per milliliter. So we have the density, and we also have the mass, but we're looking for the volume. So as it turns out, if we rearrange this equation so we can find out the volume, volume is equal to mass over density, that is going to be equal to 5.23 grams of ethanol over 0.789 grams per milliliter. And when you divide that out, it comes out to be 6.62 milliliters of C2H6O. Notice that grams is going to cancel out here, and we're going to be left with the units of milliliters. So the answer to number 5 is 6.62 milliliters of ethanol. Number 6. A gas is collected over a reaction in a balloon. When the reaction is completed and all the gas collected, the balloon is measured to have a volume of 10.6 liters at 369 K. Pressure is equal to 1.5 atmospheres. Now we're going to let this system come down to standard temperature and pressure. And if you remember, our book defines STP as 1 bar, which is essentially 1 atmosphere, at 0 degrees Celsius. So we can use our PV equals nRT to solve for, again, the number of moles of gas in this balloon. So we can see that because we're given the volume, we're given the pressure, we're given the temperature, and then R is a constant. So we can rewrite this. N is equal to PV over RT, which is equal to 1.5 atmospheres times 10.6 liters over 0.0821, that is our R constant, times our Kelvin. And that comes out to be 0.53 moles of this gas. And it's most likely a mixture, could be pure. It doesn't matter for this particular problem. So now that we know N, we can now plug it back into PV equals nRT with our new temperature and our new pressure to find what the new volume will be. So if PV equals nRT, then the volume is equal to nRT over P, which is equal to 0.53 moles of gas times 0.0821, which is our R constant, times our degrees in Kelvin. Now we changed to 0 degrees Celsius, which is 273 Kelvin. Okay, so our temperature changed there. And to note that it changed, I'll write it in green. So 273. Also, our pressure changed. We went from 1.5 to 1. So I'll write that in green as well. Now, when we multiply that through, we're going to end up with 11.63 liters. And that is our answer for number 6. Number 7. This is a question that we worked in class. The question asks us, sand is converted to pure silicon in a 3-step process. The final step being silicon tetrachloride plus magnesium goes to form magnesium chloride plus pure silicon. And it gives delta H for this reaction as negative 625.6 kilojoules per, and that is per mole. So this is going into chapter 14 when we learn about thermodynamics. It's asking us now, what is the enthalpy change when 0.608 kilograms of magnesium, so 0.608 kilograms, reacts with 2.3 kilograms of silicon tetrachloride? Okay, so the first step we need to do here is find the limiting reagent. So we can do that just by taking the amount of grams of each substance and dividing it by the molar mass. So let's do that. So if we have 0.608 kilograms of magnesium, that's going to be equal to 608 grams of magnesium. 608 grams of magnesium divided by the molar mass of magnesium, which if you look at your periodic table is 24.31 grams, is 1 mole. We are left with 25.01 mole. Likewise, 2.3 kilograms. Why does it do that? So 2.3 kilograms is equal to 2,300 grams. And silicon and this is SiCl4. We have SiCl4. This weighs 169.85 grams per 1 mole. That is going to give us 13.54 moles of SiCl4. So, now to find out which one is limiting. Well, we know we need to have twice as much magnesium as silicon. But if you look at this, if we were to divide the amount of magnesium we have, 25.01, divide it by the amount of silicon we had, 13.54, that number would be less than 2. And because of that, we know that magnesium, in this case, is going to be limiting. Now that we know that that is limiting, we can take the number of moles of that we have and find out how much silicon that we can make from it. So if we have 25.01 moles of magnesium, well, 1 mole, 2 moles of magnesium is going to give us 1 mole of silicon, 1 mole of silicon. Tetrachloride, which means we need 12.505 moles of SiCl4 to do this reaction. So now with 12.505 moles of SiCl4, we just multiply that by the kilojoules per mole. So 625.6 kilojoules per mole, and that's going to give us negative 7,823 kilojoules. That is how many kilojoules is released by reacting 0.68 kilograms of magnesium with 2.3 kilograms of silicon tetrafluoride. For a quick recap, first we found the limiting reactant. We found that magnesium was limiting. Once we found that was limiting, we found out how much of the silicon tetrachloride we actually needed. From there, we could multiply however many moles of silicon tetrafluoride we needed to use up all the magnesium by the molar enthalpy for this reaction, which gave us our answer. Okay, last question. Number 8. So the combustion of glucose, which it gives you the molar mass, 180.16 grams a mole, in a bomb calorimeter with a calorimeter constant of 5.74 kilojoules per degree Celsius. Okay, so that's how many kilojoules it takes to raise the system 1 degree Celsius. Changes from 19.3 to 61.5. Find delta H for the combustion of 1 mole of glucose. So we didn't really talk about this a whole lot in lecture, but the equation we're going to want to use here is going to be delta U is equal to the opposite of our capacity for our calorimeter times the delta T. So what that looks like is delta U is going to be equal to negative 5.74 kilojoules per degree Celsius times now our change in temperature. So our change in temperature is going to be temperature final minus temperature initial. So 61.5 degrees Celsius minus 19.3 degrees Celsius. When we solve for this, we find out that we have 242.23 kilojoules. Now, this is with burning 17.2 grams, which is not quite a whole mole. So the next step is to find out how many moles we have by how many moles of glucose do we burn by burning 17.21 grams. So 17.2 grams of glucose, 180.16 grams is 1 mole. That comes out to be 0.095 moles of glucose. Now, here we have our enthalpy for our change of U for that amount of glucose, and here's our number of moles. So now we need to take this number, the 242.23, and divide it by the number of moles. And that will be kilojoules per mole. So if we have 242.23 kilojoules and we divide it by 0.095 moles, that is going to come out to be 2550 kilojoules per mole. And that is our answer for number 8. All right, so that's all the questions for test 1. If you have any questions, feel free to email me. I will be available.